Let me share with you our course outline and the course outcomes. Academics, courses, network analysis. Okay. So let me share my screen with you. Mute. And so.
Oh my God.
All right, can you see the screen? Where is it? Just open it. So these are the outcomes for this course, network analysis. Analyze circuits using Laplace transforms. And for this particular course outcome, we had a discussion on phasors and frequency domain circuits. So this is part of Laplace transforms. Then series and parallel circuits differentiate different types of filters. So we did this for the chapter 4 actually, in which we had series parallel circuits, then Fourier series and Fourier transform, which is course outcome 3. And finally, today we'll be covering the two-port networks today. And this is a small topic, so although small, but it's important. And just to brief you about the coverage of the extended assessment, it will be covering all 4 of these course outcomes, right? So when you're measuring yourself in how much you are prepared for this course, you should measure yourself against these course outcomes. Can you analyze circuits using Laplace transform? Can you analyze frequency response in series and parallel circuits, including the board, including the filters, low pass, high pass, all that? Then apply Fourier series. You should be able to apply Fourier series and transform. In particular, I did not cover Fourier series for circuit analysis, but Fourier transform for circuit analysis. And today we'll be covering the two-port networks, right? So whenever you're measuring yourself, you should be looking at these 4 course outcomes. All right, where is it? So since I was not fully available during the weekend and all, I could not update these slides to add animations. I hope you can bear with me. So in particular, two-port networks, the topics to be covered are introduction, what are two-port networks, impedance parameters, which is called Z parameters, admittance parameters, which are called Y parameters, hybrid, which are called H parameters, and transmission parameters. So these parameters are the things that define or are used in two-port networks. Right. So what is a port? We have been working with different courses, and so port is somewhere where we do the transaction of something. Like the C port, we bring something in, we send something out. For circuits, it is a pair of terminals through which a current may enter or leave a network. So it's a pair of terminals. It's not just one, but pair of terminals. Okay, so normally what we see as an appliance, it's like a two ports only. The plug that you plug in the wall, they are normally called 2 ports. So it's not no, that's one port actually, because it has 2 terminals. The plug that you plug into the wall for any appliance, it's one port or 2 terminals circuit. But it may have 2 ports as well, like this one. It has one which is you can say the primary side or the input side and the secondary side or the output side. The example of this could be a transformer. So in a transformer, you have a voltage and current setting on the input or primary side, and then you have a secondary or the output side, which has the secondary voltage or the current. It is an electrical network with two separate ports for input and output. So one of them is the input and one of them is the output. Some of the two-port networks, there is no distinction between the input. So each end can be used as input or output. Like transformers, we can use both sides. Generally, we can use both sides. Like if it's like step up or step down. So if it's step up, the voltage from the input side is lower and the output side is higher. But if it's a step down transformer, no. If you look at from the other side, it will be the opposite, that it will act as a step down transformer, high voltage in and low voltage out, the same. One important thing is there are no independent sources within the network. There could be sources here or here, but the network part is only this part. This is the network part, right? So once again, these are sort of the intermediate networks, circuitry that connects two different sides of circuits. And we have the most important example is the transformer, I would say, in which there are two primary and secondary sides, input output side, in which we have some input power and input energy from one side, which is transmitted to the side. The transmission lines are also in two-port networks, like that. Characterization of a two-port network requires that the relationship between the terminal quantities V1, I1, V2, I2 must be expressed. So the thing is that we need to find out the relationship between V1, I1, V2, I2 to express the parameters of that network. Let's hold on. Right? Out of the four terminal quantities, two are independent. So like, as I said, if we are talking about a step up transformer, so the input side is the independent side in which we apply some voltage and some current, and it comes out to be a step up or step down voltage and current, so that are dependent quantities. Various terms that relate these voltages and currents are called parameters. As I said that in the beginning, we will be talking about Z parameters, Y parameters, H and T parameters. All right, I'm sorry I couldn't do the animation, so it's like all together. So let's go step by step. This is one example of a two-port network. Once again, this part is the network. Okay, this part is the network. This is out of the network. These V1 and V2 sources are out of the network. So it could be a voltage applied network, or also can be applied with a current source as well from both sides. And once again, the assumption is there is no independent source. There's no power generated inside the network. All right. So if we look at it in a broad sense, basically the voltage V1 is applied to the whole network, and since there is a current I1 and a current I2, so and you can see the word linear. If you remember from the linearity property, that in Fourier transform or Laplace transform, if there are two functions f1t and f2t, because of linearity, when we take the Laplace transform, we'll take independent Laplace transform, which is like sort of superposition. So we're taking each current separately. So this means we are taking a look at the I1 and the impedance seen by I1 and V1. Similarly, we will do the I2 separately from I1 and the impedance seen by the V1 and I2. So just imagine we have suppose two sources and suppose two currents. We will keep one in mind and suppress everything else, and we just find the relationship between, let's say, V1 and I2. Then maybe later on V1 and I1 separately, and then we combine them, we add them. Is that clear? We'll do this thing in a while, so don't worry. Similarly, the relationship between V2 and I1 and V2 and I2. So whenever we talk about V2 and I1, we consider I2 to be 0, for example, and V1 to be 0. Similarly, if we talk about V2 and I2, we consider I1 and V1 to be 0. So, and each of these impedances, Z11, Z12, Z21, Z22, the first one is related to the voltage or the input, and the second one, the second suffix is about the current, not the output, but the current. All right. So basically, this is the Ohm's law for individual V1 and I1. This is Ohm's law for V1 and I1. This is the Ohm's law for V1 and I2. This is the Ohm's law for V2 and I1, and this is the Ohm's law for V2 and I2. In matrix form, it's like, when we put I1 and I2 in a vector, I1 and I2. So Z11, Z12 becomes first row, Z21, Z22 becomes second row, and so on. Are you all following?
Yes, sir.
All right. Can I have a raise of hands for those who are all following?
Yes, sir.
I raised my hand. Where is it? Okay. 17, 16, 17, 18. Are there still a few guys who don't understand? Chung, Hafez, Nabihan, Mustaqim, Sarania, Fefe, I believe, is it? And who else? Yuan. Yuan is on hold. Okay, thank you for joining the class, Yuan. Guys, do you have anything to say or anything you want to ask so far? Please don't hesitate. Don't hesitate to ask. This is a simple topic, so you will enjoy doing it. Just need a basic few things. All right, so where the Z terms are called, by the way, we are doing the Z parameters, impedance parameters at this time. We are doing the impedance parameters. The Z terms are called the impedance parameters or simply Z parameters and have units of ohms. So basically this is like V equal RI, right? Some people say it's not V equal RIR, but V equal RI. And when you're doing single voltage, single current and single resistance, that doesn't make any sense. That why there is a need of saying V equal RI or V equal, but when we do impedance, we will understand that this is actually the vector V equal the matrix Z times the vector I, like this. V equals Zi. We cannot write V equal Iz, if you understand. We cannot write V equal Iz. Do you follow? Because matrices AB is not equal to BA because of the dimensions and everything. So that's why some people say it's not V equal IR, it's V equal RI, the proper way to say it. And this is the reason the first time that you're looking at it is like this. Right? Okay. Again, once again, apologies for putting everything all together, but it's not that difficult, right? So I'll just go one by one. Let me change the pointer. I couldn't even change the slide size as well. Laser pointer. All right, consider this one. Just go step by step. Do not look at this one. Just don't worry. Take this one and this V1, I1, V2, I2. And when we're talking about V1 and I1, we set I2 equal to 0. Okay, and we are only looking at Z11 and Z21, V1, I1, V2, I1. Right, so just I1 is kept and I2 is kept to be 0. Is set to be 0. Okay. Now, what we are doing here is just trying to find the relationship V1 upon I1, V1 and I1 with I2 equal to 0. So, this is where we'll apply basic circuit laws, KCL, KVL and all to find the relationship V1 and I1. Similarly, V2 and I2, V2 and I1. So you can see Z11 is equal to V1 upon I1 with I2 equal to 0. Similarly, Z21 is V2 over I1 with I2 equal to 0. Is it okay? So this is like straightforward thing just to understand and make sure that we're talking about impedance parameters and we're trying to find the parameters using simple superposition. We're just keeping I1, we're setting I2 equal to 0. I2 equal to 0. And this is only possible because it is a linear network. All right. So Z11 is a relationship between V1 and I1. Z21 is V2 and I1. And in both cases, I2 is equal to 0. Z11, what is Z11? It is open circuit input impedance. Why is it open circuit? Because I2 is 0. Since I2 is 0, this is open circuit, right? Open circuit input impedance. And Z21 is open circuit transfer impedance. Transfer means the relationship between I1 and V2. How much is I1 affecting V2? This is transferred through the network, but this is still open circuit, right? So there must be some current flowing through this part. And remember the open circuit voltage. Whenever we are looking for the open circuit voltage, we look for something parallel to the open circuit. Something must be here inside this box, and we'll find that voltage which will be equal to V2, but this is reflected because of this V1 and I1 coming from this side and appearing somewhere in some of the element here, and that's why it's called the open circuit transfer impedance. I repeat, okay, it's very simple, don't worry, it's very simple. We just are looking for impedance parameters. Z11 is relating V1 and I1, which is no problem. This is because this is like not open circuit, so there's no problem. But this one, V2 and I1, we're setting I2 equal to 0 and trying to find this open circuit voltage. So actually not finding the voltage, but using the term V2 in some expression with I1. It's like eliminating V1 and I2, which is already 0. We'll find an expression that contains V2 and I1 with this. Since this is equal to 0, this means this is open circuit. And since this is open circuit, we are looking something inside here, which is parallel to this open circuit, and we'll find the relationship. And this is called the transfer impedance, right? From port 2 to port 1. Okay? Port 2 to port 1 is like from looking from this side, but still open circuit. Yeah. All right. Similarly, if you're looking for Z12 and Z22, Z12 is V1 and I2. So obviously, just like this one, we set I2 equal to 0. This one, we put I1 equal to 0. Okay. So V1 and I2, we're looking for this V1 and finding the relationship between V1 and I2. But this time, this is open circuit here. There is no source. Just trying to find the voltage. So this means we are actually finding a voltage somewhere over here, which is parallel to this one. So this is called open circuit the open circuit transfer impedance. Whenever there is like cross, like 2-1 or 1-2, it's like transfer impedance. If it is like 1-1 or 2-2, it is just the impedance. It could be the input or the output. Give this slide maybe 15-20 seconds and see if you can find a question to ask. This is something new. So, any question? Somebody ask a question. It looks like it's similar to, yes, sure. If yeah, it is like that. Except in superposition, we are finding the values because we are putting V2 equal to, let's say, 10 volts. I1 is this much, and we put and like doing superposition, suppressing something. We don't put the values, but we find the expression. And that expression will have a value. So there's it's always a ratio because we're looking for these parameters. Z11, Z12 and all. We are looking for these parameters. All right, anyone else? Thank you, Heng Chin Dian. Anyone else? All right, welcome. Okay, so we proceed. Since the Z parameter, once again, I apologize for the mess. I don't like a slide that shows everything all together and with such bad graphics. So I got these slides. I have always refurbished them and tried to improve those slides. But I'm sorry, I have to use the old ones. Since the Z parameters are obtained by open circuiting the input or output port, they are called open circuit input impedance. The open circuit impedance parameters. So we just already explained that part. When Z11 is equal to Z22, so it is possible to have Z11 equal to Z22. It is possible. The two-port network is said to be symmetrical. Okay. When the two-port network is linear and has no dependent sources, the transfer impedance are equal. Z12 equals Z21, and the two-port is said to be reciprocal. Okay, so once again, if Z11 equal to Z12, if these two are equal, so this could be an equivalent circuit of a two-port network. Notice that there is no independent source inside it. Okay, which is the condition from this slide. There are no independent sources in the network. So there are no independent. There could be dependent sources. All right. When the two-port network is linear and has no dependent sources, so no dependent sources, the transfer impedances are equal to Z12 equal to Z21, and the two-port is said to be reciprocal. Reciprocal because you look from this side or this side, they will be the opposite, I believe. Okay, this is just informatory. All right, so we take again, this is all coming all together. So I want everything to be step by step, but hopefully you can forgive me for this one. Determine the Z parameters of the following circuit. So this is a very simple circuit. There are no dependent or dependent sources inside for sure, but it has two terminals here and two terminals here. That's why it's called a two-port network. Let me use my I have my device today. So let me share screen, and I can come here or here, and all right. So if I keep it like this, this is the two-port network, right? This is the two-port network in which there are two terminals here and two terminals here. So this is a two-port network. Whatever is inside is not always known. That's why we want to find out what's Z11, Z12 and all. Okay. We want to find out so just notice that these are not the impedance parameters. Okay. We are finding it using this expression or this expression and so on. Okay, let me just put at least one box. All right, this is the two-port network. So whenever we're finding Z11 equal V1 over I1 with I2 equal to 0. So I2 equal to 0 means that this is kept as open circuit. Okay, so we just find V1 over I1. We just try to find V1 over I1, which will give us the Z1. So basically we're looking at the impedance from this side, kind of the impedance from this side, and we can see that since this is this part is 0 because of open circuit, so this resistance is not considered. Whatever is left is just this as the impedance, which is 60, and you can see that Z11 is 60. I repeat for maybe the other V2 over I1. Okay, now let me remove all the ink. Oh, where is it? This one. Okay, let's consider V2 and I1. So V2 and I1, again, this current is equal to 0. So this is again, this part is again open circuit. Okay, and we just look at the circuit. Okay, remember that when we were looking for, let me go back, when we were looking for V2 and I1, V2 and I1, which one is it? V2, I1, this one. So we look for the impedance seen from this side. Okay. So V2 and I1. Does V2 see the 20 ohm resistor? Let me remove all the ink. This is mostly, it is like common sense kind of thing. If we look from this side, does V2 see any effect of this and this, I1 and 20? What do you think? Oh, yeah. Guys, can I get a feedback from you guys that, yes, Jocelyn, you're right. There is no effect of this 20 ohm because we are looking at this I1, which is flowing in here. Okay. And V2 is only looking at this one. It does not have any effect of this 20 ohm. Previously, we were looking from this side. It was including everything from this side. That's why 20 and 40 were kept together and were in series. But this time, since it is only looking at it from this side and it's like 40 ohm only, that's why you can see that Z21 is 40. Okay, this is mostly it is like common sense, so don't worry about like finding the right technique. Then V1 and I2. V1 and I2. So when we look from this side, V1 and I2, the impedance, does this 30 and I2 has any effect on V1? Because this current is flowing like this, although there's no current anyways, but this current is still there. We see only 40, right? That's why this is 40. Is that clear?
Yes, sir.
Everyone? Everyone? And finally, V2 and I2. V2 and I2, in this case, I1 is 0. This is 0. So we can easily say that this is like 30 and 70. That's why it's 70. Right? And just don't forget this ohm is there as the unit for impedance. Give yourself 30 seconds to digest this. Right? Okay. Let's just go in detail if someone wants to do it in completeness. Please move forward. Okay. So this is the same example. Okay. This is like done properly. So you can see that this part is Z11, V1 upon I1 with I2 equal to 0. Okay. Can we find V1 from the circuit? The V1 from the circuit. So V1 is this voltage, right? And since this part is 0, I mean, you cannot see my pointer. This part is 0, so only this circuit is there. So what is V1? V1 is IR, right? I1 times 20 plus 40. So 20 plus 40 times I1. So 60 I1 upon I1, 60 ohm. If you don't understand, let's take a look at the second one. Second one is V2 over I1. Find V2. So V2 is, since this is open circuit here, this is open circuit, we look for something parallel. So this is parallel. Okay, how much current is flowing? I1 is flowing. I1 is I1 and the resistance is 40. That's why V2 is 40 I1. Divided by I1, we get 40. Let's move to the next one, V1 over I2. So we're looking at this particular voltage, which again, now this is 0. So we're looking at this voltage. Remember that whenever we're looking for open circuit voltage, we look for something parallel. So what is the voltage across here? It's like I2 times 40 because there's no current from I1. It's I2 times 40. V2. Oh, sorry, so yeah, 40. I will look at this one. 40 times I2 upon I2, so that's 40. And similarly, when we look for V2 or I2, V2 or I2, yeah, I'm sorry, I was looking, I mentioned, yeah, it's okay, correct. V2 or I2, V2 is like this voltage, okay? This voltage is like all of this thing, so I2 times 30 plus 40, 70 I2 upon I2, we get 70 ohms. Anyone, any question?
No, sir.
Only one guy is speaking. Are you representing everyone? Who's speaking? Is it Heng Ching? No, Chong. Who's saying no, sir? Is it Chong? No, you will not say anything. All right. So I think this is like very easy stuff. I think. Let's move to the okay. Determine I1 and I2 in the two-port network shown. Now we are given the impedance parameters and we want to find the I1 and I2 where the voltage are given, the source is given, so we need to find the I1 and I2. Yes, I1 and I2. Okay, V2 is not mentioned here. Okay, no problem. So you can see that what's given here is basically the impedance parameter, the Z matrix. Z11, all this Z, just like this one. This matrix is given, for example. Okay, and we have all these formulas as well. And this particular matrix means this equation. Okay, so this is basically this equation written here. V1 is Z11 40 ohm times I1 plus Z12 J20 times I2. Is it okay? Is it okay, guys? Similarly, V2 is Z21 J30 times I1 and 50 I2. V1 is already given 100 angle 0, and V2 is, since we have this one here and it's like this is the current flowing, so the voltage here is minus 10 I2. Okay, at this point in time we expect that the basic calculation or inferences from the circuit is straightforward for you. So because this is like chapter 17, 18, chapter 19 of the book. So this is like baby stuff, that how to expand this matrix into these equations and to say V2 is minus 10 I2. I believe you all follow that. Why is it minus 10 I2? Because it's like opposite direction. The current is going here and we're looking for this voltage, so it's like minus 10 I2. But if there is anyone, please don't hesitate to ask. I will not insult anyone. Trust me. God promise. Anyone? Today, I don't hear Parin today. Are you here today, Parin?
Yes, again.
I don't hear today. I like you because you speak up in the class, even though Nobody else is speaking, but you always speak. Okay, good. All right. So, yes, go
So
ahead.
Excel or finance will just be like that. So you don't have to find the I1 and I2.
In this one, you have to find. This is not done yet.
Oh,
Yeah.
okay.
Okay. Yeah. So now it's actually almost done. This was the main difficult or sort of difficult thing, that you need to write equations. We can place V1 here, and what else? V2 as here. So we have two equations and two unknowns. Find I1 and I2. What? How else this could be? How easier? How much more easier it could be in writing and finding the values, right?
Yes, sir.
So please, everyone, there is like free marks for you in this particular question. Don't miss out. So just like putting the values here and here and solving and finding. One thing maybe I didn't mention, but you guys should know is whenever there's a question and the variables are given in a particular format. For example, in this one, the voltage is given in 100 angle 0. So this means the reference for the circuit is phasors. So you should also answer your values in phasors. If it was like the voltage was like 100 plus J40 or 10 cosine 20 J omega T, something like that, you should also answer your variables answer into that particular form. Don't miss this out. It's a good habit. All right, so another one. So they have given you the impedance parameters, and we need to find I1, I2, V1, V2. So again, the same thing, that you will be putting this one equal to 0 for V1, Z11 and Z12 and Z21, and similarly you will put this current to be 0 for the other side, and you can find the values. Okay. And surprisingly and amazingly and amusingly, everything is the same except it's like admittance. So we are keeping I equal YV. So this is the Ohm's law for the admittance. All right, this is called admittance parameters. So everything very same, everything similar. It's like the reciprocal of impedance, and we will write it in this form. Okay, so I'm not. This is all the same, except you see this is all reciprocal. I'm not sure if they're actually individually. Yes, I'm sure. If you look at the matrix, yeah, if you look at the matrix, individual matrix y11 or y22 or y12, they are reciprocals of z11 individually, not the whole matrix. They are individual reciprocals of z11, z12, z21, and z22. So if you somehow forgot what is admittance, you can find impedance parameters and take reciprocals of each term to get the admittance parameters. Right? So don't worry. So I'm skipping this part. Same thing. And same thing. And same thing. And same thing. Hybrid parameters. So the name is like Honda Accord hybrid, which runs on gas and like battery, but it's just like hybrid means it could be anything. So you can see that V11 is H11 is V1 upon I1, but H12 is V1 upon V2. So it's like hybrid means it's a mix. It could be anything. It could be anything over here or anything over here. So that depends on the need. They can change. They can have both I1 here as well. So it's like a mix up. So these variables can change the places. But now this is not impedance. This is not impedance. This is not. This could be anything. It could have a unit. It could not have a unit. It has a different unit. See, different unit. So if it is, for example, H21, Can someone tell me what are the units of H21? Can someone tell me what are the units for H21? What are the units for H21? No unit. Yes, done. Very good, because who showed a surprise? Is this a surprise or a yawn? Justin, are you yawning? No unit. Why? Done.
Cancel out.
Cancel out, because it's like I2 and I1. H21 is basically I2 over I1. But if we talk about H22, what are the units of H22? Jocelyn? Yes, so it's like, shall we keep it like that, or what is V upon I or I upon V? Admittance. So it's like a mho, this is how we write the like inverse omega. Somebody was very creative in suggesting this unit for, this it's like this, ohm and mho. Wow, very creative, huh? Okay. Any question for this one? So basically, you need to find a relationship in the circuit to just fix things together. It's like matchmaking. Just pick the variables, find the ratio, and you will get those parameters. Play around, and you will have lots of fun. All right. These are some names that some genius gave it to them. I'm not interested in. All right. Okay, I think once again, straightforward things. You can do these examples very easily. What else? Transmission parameters. I don't think I'm gonna cover this because yeah, I'm not covering this. It's okay. What else? That's it. The good thing is I'm done with my topics for today. Luckily, I not enough to be covered today, and I couldn't also prepare more things. So we will, let me just make it easy for you. So this slide, this card. I just slash out. Cannot. Why? I can do this. Okay. Any question, guys? Any question?
None from me, sir.
Very good. Actually, very bad. Should I be asking questions? So actually, this is it for our network analysis course. I think we did good speed in a way that we have one week and a tutorial left to do a good revision. All right. Tomorrow's tutorial, I'll try to do some of the questions from your Fourier series, Fourier transform, and maybe one question from two-port network. Next week, I'll keep complete for your revision. So you have a whole week next week in which you can ask any question from anywhere from our syllabus, and we try to solve them in the class, or maybe discuss them in the class. And next week we'll have our test 2 as well. Test 2 will cover chapter 4 and like the filters, Fourier series, Fourier transform. Okay, I already mentioned. Chapter 3 is Yeah, chapter 3, 4, 5. Is it? I think chapter 3, 4, 5. Oh, just for. Chapter lectures. Chapter 3. Yeah, 3, 4, 5. Yes. And for preparing you for the two-port network, I think I'll take a quiz next week to ask questions about the two-port network. All right. Any question? Yes, Nazirul. Yes. For the Fourier transform tutorial, okay. Are you asking something or just maybe just okay? I don't think that everyone have submitted for Fourier series. I'm talking about Fourier series so far. I have not given you the questions for your Fourier transform, which I'll give you today, and we'll discuss them tomorrow. So let's relax it a bit for you guys as well. We will have the submission for Fourier series and Fourier transform probably by Friday this week, because I know that might take some time. So don't rush out, don't rush. Take your time in doing Fourier series and Fourier transform questions. I will post the questions for Fourier transform today, and you'll have until Friday to submit. If that because we have not done the tutorial for Fourier transform yet. That's why. If that answer your question. Is it okay? Okay. Anyone else? So may I ask test 2 will be on which day? Okay, maybe we can have a poll here right now. Test 2. Okay, how about I want to have a review as well so that we can discuss test 2 once it is done, and you can curse me. But then we have to have a session after week 12. Is it okay if we have a half an hour session in week 13 so that we can discuss test 2 as well? If you can allow me to have a session in week 13, then maybe I will take the test on Friday next week, test 2. Is that okay? Everyone, is that okay? Let's do a quick poll. Jocelyn, can you make a poll that test 2 Friday and test 2 review Tuesday week 13? Test 2 Friday week 12, review test 2 Tuesday week 13. Okay, so I will be needing some time to grade as well. Can we have which Monday? Coming Monday? Okay, I'm okay with that. Week 12 Monday? We need to do it during the exam. You mean week 12? Next week is week 12. So Tuesday, test 2, Tuesday, week 12. Is that okay? Tutorial session. Tutorial session. So many options now. People are gonna play, especially one guy who will play with all these options. I know. Just keep it Tuesday. See. Okay. Guys, I don't know. Okay, so Ong, can you please ask in the group? I know there's a private group as well. You can ask in your group that, okay, which day is suitable for you? Whatever day it is, let me know. Lukman, are you in this group? Because Lukman is not from this batch. Is Lukman here? Lukman, please make sure that you contact Ong if you're not in the group, that you can have. Yes, please. Oh, thank you, Ong. So just everyone, please discuss with Ong and see what. Yeah, there will be something every day, guys. You know, it's a semester system. It is like that. So at this time, I'm stopping the recording. Okay.